Hello, let's understand how we can understand the shear fracture happening when we do the impact testing. Okay, so guys, you understand that the impact sample looks like this. Okay, so the impact sample has got dimension of 10 mm here, 10 mm here, and this is 55 mm. Okay, this is the normal uh, impact test. Okay, sample where the V notch is at the center, right? So we place it under the machine and we allow the force to hit over here, and what happens in turn, this breaks, right? After breaking, this is the type of phase. You can see we'll take one part of this of the breakage, then we can see that it can be of any kind of nature here. Okay, now we understand that this fracture happens through two mode. One is shear and another is called as brittle. Okay, one is the shear and one is the brittle. Brittle will have smooth surface and shear will have dull surface. Okay, understood? Okay, now so how can you identify this one, and how can you say that how much amount of shear it is happening over there? Okay, so what is the amount of shear or what is the amount of brittle, that is also called as crystalline. Okay, now let's see that if you see option A or the first case here, if you try to see, so this black portion is your notch portion. Okay, this notch portion, this notch has got depth of 2 mm, right? So this complete length is your 10 mm, but out of this 10 mm this black portion is of 2 mm, and this side it is complete 10 mm. Okay, now we can see that in the middle portion, basically in the middle portion we can see that the surface is quite smooth, right? There is no any dull surface. The dull surface is only at the periphery, right? Okay, so that's what we measure through this method. So this is the typical show which has been drawn for the impact sample. So this is the notch. Okay, this portion is the notch, and in the middle it is supposed to have the brittle fracture. Okay, so this brittle fracture region we calculate. So through this method of by measuring A and B, we assume that this one is of kind of rectangle, and we measure this A and B. So A and B we put over here, A and B. Okay, so this is given in inch. So just remember that this is given in, this table is given in inch, so we can convert this table in mm. Okay, no problem, that conversion can be done easily. Or you measure in mm, you convert it into inch, then you can compare that what is the amount of that shear or that thing will happen. Okay, now so we can see here, if you take this portion, right? So like A and B, if you try to measure, right? So A and B will be such that your this portion is your B. So B can be complete 8 mm. Okay, and your A will be slightly less than 10 mm. So suppose let it be like 9 mm. So like 8 mm and 9 mm it will be, right? So 8 mm and 9 mm, so 8 mm is the full length, so that is equal to 0.31, and if you see 9 mm, so 9 mm will be somewhat lesser than this 0.4, so we can see that it is falling like 9 or 5% between them. So like this you can measure. So by looking at this photo we can see that there is 10% shear is happening over there. Okay, now if you see in the next portion, so basically you can see that this shear zone has increased, so we can say 20%, then 30%, 40%, 50%. You can see the shear zone has formed, and this is significant, right? Now for this 60%, this is the case, 70%, this is the case, 80%, 90%. So you can see the brittle region is getting low, right? And in the last portion there is no any brittle region. There is somehow some small things are there, but that can be ignored, right? So that's what it is also shown over here. So you can see when it looks completely basically like brittle fracture, then we can say here around 10%, because the other things are very difficult to measure. Then 20%, some more thickness it has got, then other more thickness, more thickness, more thickness, more thickness, right? Like this. So this is the standard, that ASTM A370, which tells like how to measure the amount of shear fracture in this. Okay, so this will be helpful for those who are working in laboratory, so they must be doing these things. Okay, and basically this measurement is also used for DBDT, ductile to brittle transition temperature, or in industrially generally this FATT is used, fracture appearance transition temperature, right? So where we mark the percentage fracture through crystalline. Okay, it would go like this, and correspondingly the temperature is recorded, right? So this is the mark at 50% crystalline and 50% shear. Basically we get this FATT. Okay, so this is the method. So this technique basically helps to understand what is the FATT. So in that case we'll take the sample 1 and we do the breaking at like suppose 20 degrees centigrade, then sample 2 by increasing the temperature, right? So like 40 degrees centigrade, 360 degrees centigrade, like this, and we will go to negative direction also, like -20, -40, and in each sample we'll measure what is the amount of shear and what is the amount of crystalline. Okay, and through that we can say that at what temperature we are getting the FATT. Okay, so this is the method. So thank you all.